Hello and welcome everyone to today's NPTEL live session on the course of Foundations of Cryptography. So let me share my screen. So as I do every week, first I will discuss the assignments given for week 7 in the NPTEL web page. And then after that we will talk about today's topics mainly. Okay. So about the assignment, first question in the assignment was choose the correct options from the following. If an encryption scheme is an authenticated encryption scheme, then it is also CPA secure. If an encryption scheme is CPA secure, then it is also an authenticated encryption scheme. A secure authenticated encryption scheme cannot be constructed using a malleable encryption scheme. And then a secure authenticated encryption scheme is necessarily CCA secure. So let us first just recall once what is authenticated encryption scheme. So basically, in general, in CPA secure encryption scheme, what we do is that we achieve basically secrecy of the underlying message in presence of encryption oracle, right? So adversary has access to an encryption oracle. By encryption oracle, what we mean is that adversary can give plain text of its choice to the oracle and get back corresponding encryption of that message, right? And using, even after having access to that encryption oracle, the adversary cannot significantly distinguish between encryption of some message M0 and message M1, where both M0 and M1 are known to adversary, but when it is given encryption of any one of them, it cannot tell with significant probability that whether it is seeing an encryption of M0 or encryption of M1, right? So that is the concept of CPA security. Now what then we move to the concept of CCA security, where we say that the adversary has access to a decryption oracle as well, where it can give to the decryption oracle ciphertext of its own choice, with a restriction that it cannot query the decryption oracle with the challenge ciphertext itself, right? And then with the access, even with the access of this decryption oracle, the adversary cannot distinguish encryption of M0 from encryption of M1 with non-negligible probability. That is the concept of CCA security. And then we move forward to authenticated encryption, where apart from CCA security, there is another concept of ciphertext integrity, where we actually allow the so we basically, what we want is that the adversary should not be able to produce some valid ciphertext such that that ciphertext is not seen by the adversary previously through the query phase, like by the response of encryption oracle, whatever ciphertext it has seen, this produced ciphertext should not be same as any of them, and also this ciphertext should be decrypted to some valid messages, which are not also this valid message also should not be same as any of the messages that it has seen previously, right? So that we call the property of ciphertext integrity. So what authenticated encryption scheme provide is that both CCA security and ciphertext integrity. So now let's look at the options. First option is saying that if an encryption scheme is authenticated encryption scheme, then it is CPA secure. So as I just said, that authentication encryption scheme provides both CCA security and ciphertext integrity. And if an encryption scheme is CCA secure, then it is definitely CPA secure. So of course, first option is correct. Then the next option says if an encryption scheme is CPA secure, then it is also an authenticated encryption scheme. We cannot say that, because CCA security is more advanced concept than CPA security. So CPA security does not necessarily mean CCA security, and neither it means ciphertext integrity. So the second option, of course, is not correct. Now the third option says that a secure authenticated encryption scheme cannot be constructed using a malleable encryption scheme. Now, what malleable encryption scheme means is that you can, so after, let's say, you are the adversary is seeing the challenge ciphertext, then it can like it can modify the challenge ciphertext in such a way that that modified ciphertext also, after passing to the decryption oracle, gives back some meaningful message, and from that it can basically somehow comment about whether the challenge ciphertext encrypts M0 or M1, right? So that is that is what is meant by malleable encryption scheme. Now, what we know about secure authenticated encryption scheme is that it needs both CCA security and ciphertext integrity. Okay. So, so basically, using malleable encryption scheme, which may basically mean CCA security. So, this option says that authenticated encryption scheme cannot be constructed using malleable encryption scheme, which is wrong. Okay. So basically, if you have a malleable encryption scheme which is secure, that means that this encryption scheme is CCA secure. Okay. Secure malleable encryption scheme means that the ciphertext can make use of the decryption oracle, but still that scheme remains secure. So that means you have a CCA secure encryption scheme, and now with that you can to ensure ciphertext integrity, you can augment that scheme with some other mechanism. So we cannot say that secure authenticated encryption scheme cannot be constructed. You can construct basically. Okay. And the fourth option is secure authenticated encryption scheme is necessarily CCA secure. Yes, this is correct, because secure authenticated encryption scheme, of course, satisfied both CCA security and ciphertext integrity. Okay, so last option is correct. Proceeding to the next question. Select the incorrect options. To break the security of a cryptographic construction which is provably secure in the ROM model, that is random oracle model, one must discover a weakness in the actual hash function. So, which is of course true, because as we have discussed the random oracle model last week. So what random oracle model does, it acts like a like bridging the gap between provable secure construction and practically efficient construction, right? So if you can prove the security of some cryptographic primitive in the random oracle model, that means that when you implement that scheme practically, you will basically instantiate that random oracle with some secure cryptographic hash function, right? Now, to break the security of cryptographic construction, you have to basically break the security of the underlying hash function. But if you use some secure hash function as the to instantiate the random oracle, then basically you are done. So, so this is true that if you have to break cryptographic construction which is provably secure in the ROM model, then you have to discover weakness in the actual hash function. You have to attack the hash function basically, because otherwise the provably secure cryptographic construction in ROM model just signifies that apart from that assumption of random oracle, you have all the other things in the primitive which are secure. Okay. Second option says there does not exist any ROM based cryptographic primitive that is efficient and highly secure. That is wrong, because there are already many ROM based crypto primitive existing where you instantiate ROM with some secure and efficient hash functions, and those primitives are practically efficient and of course secure. In the ROM model, unique queries are always answered with unique answers. This is wrong. Basically, what ROM model does is that you query the random oracle with some input and you get back the output, and the output seem to be random to you or the adversary. So basically the outputs of the queries should remain uniformly distributed over the output space, and the output should be independent of each other. So even if your queries are related to each other, the output should not be. Okay, so all the outputs you see by querying the random oracle should be independent of each other and uniformly randomly distributed, right? There are schemes secure in the RO model, but insecure when using any real-world hash function. So yes, that is true, because we have already stated that when you instantiate a random oracle with hash function, if that hash function is not secure, then basically the practical instantiation of that scheme, although probably secure in the RO model, is not secure in practice. Okay. So let's proceed to the next question. If you have any query, you can just unmute yourself and ask. Okay. Now, let pi, which is consisting of three protocols, JAIN, ENC, and DEC, be a symmetric key encryption scheme with message space M. We construct a new symmetric key encryption scheme pi dash, which consists of the JAIN dash, ENC dash, and DEC dash for message space M square as follows. The key generation algorithm JAIN dash outputs K, which is combination of K0 and K1, where JAIN dash basically invokes two independent instances of JAIN to output K0 and K1 respectively. And encryption happens on message M0, M1 such that ENC dash M0, M1 with respect to key K output C0, C1 as the ciphertext, where C0 is ENC of M0 with respect to key K0 and C1 is ENC of M1 with respect to key K1. The decryption algorithm also decrypts in according manner. Okay. Now there are some statements you have to choose which are the correct. First, it says that the scheme pi dash provides ciphertext integrity. Now, if you remember what ciphertext integrity means, is that we just discussed, right? That the adversary should not be able to output some valid ciphertext in such a way that that ciphertext has not been seen by the adversary previously, and that ciphertext decrypts to some valid plain text, right? Now, if you see this particular scheme, let's say your through the encryption oracle query, the adversary basically sees encryption of M0, M1 as C0, C1, right? Where C0 is the encryption of M0 and C1 is the encryption of M1. Now, what adversary can do possibly is that it can query the encryption oracle with message M0, M1 to get ciphertext C0, C1, and it can query the encryption oracle with some M0 dash, M1 dash to get the ciphertext C0 dash, C1 dash. Okay, where all M0, M1, M0 dash, M1 dash are distinct plain text. Now, the ciphertext can easily come up with ciphertext C0, C1 dash. Okay, now C0 was encryption of M0, right? And C1 dash is valid encryption of M1 dash with respect to key K0 and K1 respectively. Okay, so surely C0, C1 dash will be a valid encryption of M0, M1 dash with respect to key K0 and K1 respectively, or with respect to the scheme ENC dash. Okay, so and of course M0, M1 dash is not a valid plain text, right? So the adversary is able to come up with some new ciphertext here. So we cannot say that ciphertext integrity is maintained by the scheme PIDAS. Right, mix and match attack. You can say that. Now the next option says that if pi is multi-message COA secure, then PIDAS is also multi-message COA secure. Now notice that what is COA security? That is ciphertext only attack. So adversary is able to see the ciphertext only through the communication channel, public communication channel. Apart from that, it does not have any access to encryption oracle, decryption oracle, nothing. So it just sees, passively sees the public channel and gets to know the ciphertext. It does not even know the corresponding plain text, right? Now in ciphertext only security, if pi is multi-message COA secure, so what PIDAS provides as extra information to the adversary here. So basically, it if you see the communication channel for the scheme PIDAS, it will basically consist of many ciphertext which are encrypted using K0 and many instances of ciphertext which are encrypted using K1 with respect to the basic encryption scheme ENC, right? So in case of when an adversary is looking at the communication channel, in case of the scheme pi, there it will be able to see multiple message in one session, basically multiple ciphertext in one session, which are encrypted using the same key, but which are encrypting multiple number of messages. Okay. Now, in case of PIDAS, it is the same scenario. It's just that you are seeing two set of ciphertext. One is with respect to some key K0 and another set of ciphertext of different messages with respect to key K1. So it's just that you are getting the adversary is getting to see ciphertext with respect to two different keys, nothing else. Okay, so basically, if pi is multi-message COA secure, PIDAS will also be multi-message COA secure, because the adversary cannot effectively use any kind of other information to get to know the any extra information about the underlying plain text. Okay. Then coming to the third option, if pi is CCA secure, then PIDAS is also CCA secure. Now, remember that CCA security needs provides the adversary with the access to decryption oracle, right? Now, even if pi is CCA secure, we say that PIDAS is not CCA secure. Why is that? Because basically what using the decryption oracle access, what the adversary can do in case of PIDAS, let's say that the adversary gets to see the challenge ciphertext, which is C0 star C1 star, which can be encryption of either M0M1 or encryption of M0-M1-. So basically, challenge plain text chosen by the adversary are M0M1 and M0-M1-. And the challenger encrypts any one of them and outputs the ciphertext C0 star C1 star. Okay. Now, what the adversary can possibly do is that it can again let's say it chooses M0 M1 and M0-M1- in such a way that M0 is equal to M0-, okay, and M1 can be anything. Now, when it sees the ciphertext C0 star and C1 star, it remains to see just whether that C0 star is encryption of whether C1 star is encryption of M1 or encryption of M1 star. Okay, so then basically it in place of C1, then it keeps C0 as it is, like C0 when it is querying the decryption oracle after in the post challenge query phase, then it keeps the C0 part exactly same as the challenge ciphertext C0 star, and it changes C1 to some encryption of M1 previously seen from the encryption oracle. So necessarily the decryption oracle query should not be equal to the challenge ciphertext. So it will not be same as challenge ciphertext, but it will be C0 star comma some C1 double dash. So that C1 double dash is some encryption of M1 seen previously from the encryption oracle by the adversary. Now when the decryption query output comes, then it will match whether that output, the second part of the output is the output of it outputs M1 or not. Okay, if it outputs M1, then it knows that the challenge ciphertext actually encrypts M1, otherwise it encrypts M1 dash, right? So using this decryption oracle service, the adversary is able to determine whether it is seeing encryption of the first message or the second message. Okay. So that's why we can say that pi dash is not CCA secure even if pi is CCA secure. Okay. And then the fourth option is if pi is CPA secure, then pi dash is also CPA secure. This is again true because just in the similar way as we argued for multi-message COA security, here also in case of CPA security, the bunch of ciphertext it can see using the encryption oracle is nothing but set of ciphertext under key K0 and set of ciphertext under key K1 with respect to the basic scheme pi. Okay. So that's why there is no extra information available to the adversary which it can exploit through using the encryption oracle. Okay. So if pi is CPA secure, then pi dash is also CPA secure. Coming to next question. Choose the correct combination for commitment schemes. 1. Receiver. So there are left column and right column. Can you please repeat the explanation of multi-message part? Okay, for the previous question. Right? Okay. So what we argued, just remember that in case of what happens in case of multi-message COA security, we say that the adversary is looking at the public communication channel where in a single session, the adversary is able to see multiple ciphertext which are corresponding to multiple plain text, but they are encrypted using the same key K. In case of pi, which is the basic and secure symmetric key encryption scheme here, right? So now when we come to the scheme pi dash, then what the adversary is able to see, if you look at the format of ciphertext here, the format of ciphertext is C0, C1 for each message, which are again of the form M0, M1, right? So in multi-message COA security case, in the public communication channel, there will be a set of ciphertext available to the adversary, which it can see at once. You can say of the form C10, C11, which is the first ciphertext, then C20, C21, second ciphertext, C30, C31, third ciphertext, and so on. So there will be a set of ciphertext in the public communication channel seen by the adversary at once. And how each of these CI0, CI1 are computed? Each of these CI0 are encryption of MI0 with respect to key K1, and each of CI1 is encryption of MI1 with respect to key K1. Okay. Now, if you see this, this is nothing but you can arrange them as two set of plain text, two set of cipher text. One is all the ci zeros for I equal to 1 to say q, and a set of cipher text ci1 for I equal to again 1 to q. And this first set ci0 for I belonging to 1 to q, they are nothing but same as what the adversary would have seen in multi-message COA security game of pi with respect to key K0. And the second ciphertext set CI1 for I belonging to 1 to Q is nothing but the set of ciphertext that the adversary would have seen in case of multi-message COA security game of the basic scheme pi with respect to key K1. So these are just two different set of ciphertext with respect to two different keys of different messages. So if pi dash is able to gain some extra information about the underlying message of each of these part, okay, if it gain information of by seeing ci0 ci1, if it gains information about underlying mi0 mi1, then it can use that information to break the multi-message COA security of the basic scheme pi, which is not true. Pi is already assumed to be multi-message COA secure. Then of course we can argue by contradiction that pi dash is also multi-message COA secure. Hope I am clear. Okay. Okay. So proceeding to the next question, choose the correct combination of commitment scheme given below. So there are this left column and the right column. You have to match them. So the right column says about hiding property, binding property, and provides opening information, accept or reject data M. So if you remember how commitment scheme works is that there is this two party, sender and receiver. Sender is trying to hide some message M inside a commitment C and sends it to the receiver. And when required, the sender provides the opening information to the receiver. And what receiver does is that using that opening information, it can basically check what is the underlying message of the commitment. Or in other words, it basically gets some message comma some randomness information such that the receiver itself computes what would have been the commitment if the underlying message is M and underlying randomness is R, and it calculates the commitment and it matches the commitment with the commitment received from the sender. If it matches, then it accepts the message M as the underlying message of that commitment. Okay, now there are two security properties which have to be satisfied by commitment scheme. One is hiding property, another is binding property. Hiding property is necessary when the sender is corrupt. When the sender is honest and receiver is corrupt. So basically, when we compute some commitment C of message M, then we want to hide the information M. So one who is seeing just the okay, the meeting will end in 10 minutes. You can join in the same Zoom link. Okay. Now, whenever the sender is honest but the receiver is corrupt, then the receiver, after receiving the commitment C, it can just want to guess or want to retrieve what is the underlying message M without the opening information. So only the legitimate receiver is going to get the opening information, and using that opening information, it can basically check what is the underlying message of the commitment. Until and unless the sender is providing the opening information to the receiver, till then the receiver should not be able to gain any information about the underlying message just looking at the commitment. That is what the hiding property of commitment scheme requires. And the binding property of the commitment scheme handles the case when the sender is corrupt but receiver is honest. Now, what sender could possibly do if it is corrupt is that it first come up with two message and message randomness pairs such that message M1 and randomness R1 gives you the commitment C, and some other message randomness pair, say M2R2, gives the same commitment C. So what it does is that it sends to receiver the commitment C, but when providing opening information, it sends to receiver the pair M2R2 instead of M1R1, and the receiver verifies whether the commitment generated from pair M2R2 is equal to the commitment that it received from the sender, and the test passes in that case. So basically, actually communicated information was M1, but receiver gets the information as M2 because both the information actually map to the same commitment. But this should not occur. Binding property ensures it is very difficult to come up with these two different pair of message randomness such that both of them, when committed, will return same commitment. Okay, so this should not happen. Now, I guess all the questions will be answered from this discussion. So let's see. Receiver basically accept or reject data M, right? It verifies whether the message randomness pair, the opening information coming from the sender, matches with the commitment that it received from the sender. If it matches, it accepts the underlying message M. Otherwise, it rejects. Okay, so 1 matches with 3. Corrupt sender, honest receiver matches with binding property, as I already discussed. Honest sender, corrupt receiver matches with hiding property, that also I discussed. And sender provides opening information. So our option goes 3, 4, 1, 2, right? So that is the first option. Next question, let E of K comma M and D of K comma C. So obviously E is encryption scheme, D encryption algorithm, D is decryption algorithm, K is the key, M is plaintext, C is ciphertext. So for key, where K is n-bit binary string chosen at random, be a crypto system that provides authenticated encryption. Consider the following constructions and choose the correct option. So there are two modified constructions given. First one says, modified encryption algorithm E1, taking key K and plaintext M maps to ciphertext C, C, where C is encryption of M using key K using the basic encryption scheme E. That is the encryption algorithm. And decryption, what it does is that it takes ciphertext C1, C2 using the key K. It returns just decrypts basic decryption algorithm with key K and ciphertext C1. Okay, so let us first look at the first construction. So whether it will be, so there are comment about CPA security, ciphertext integrity, CPA security and ciphertext integrity, right? So, so in the first option, you can just see that there is no when the modified decryption algorithm D1 takes some C1, C2 pair, it does not check whether C1 is equal to C2. Basically, by a valid encryption algorithm, both the part C, C should be same, right? So, but here in the decryption algorithm, there is no such check like that. So, when considering the CPA security scenario, basically in CPA security scenario, the adversary has access to some encryption oracle, right? So in case of, so let's say it has this two plaintext M0, M1, and the challenge ciphertext is some sister, encrypting either M0 or M1. right? Now, if we say that this scheme is not CPA secure, that means it has to make use of the encryption oracle to distinguish between encryption of M0 and M1, right? So see that we argue that in case of 1, it just the modified scheme E1 actually does not provide any extra information where the adversary is able to use the encryption oracle to exploit about the underlying information. So if the basic scheme is CPA secure, through the encryption oracle service, the adversary is just able to get to see plaintext ciphertext pair as C comma C, where each C comma C is encryption of M only. So if it would have access to encryption oracle for the basic scheme E, then it would have seen the same M comma C pair, where in case of modified scheme E1, it is just seeing M comma C pair. So basically no extra information is leaked about the plaintext by the ciphertext. So we say that it is indeed CPA secure. But whether it is ensuring the ciphertext integrity, so here also we say that the adversary can come up with some C1 comma C2 pair where it knows C1 is some encryption of valid message M2, and it can just output C1 comma C2 where C2 need not be any particular valid encryption of any message. C2 can be any random ciphertext from the ciphertext space. But if C1 is a valid encryption of M1 already known by adversary, then it can provide C1 comma C2 as a valid ciphertext, because the decryption does not even care of what is the second part of the ciphertext. It just takes the first part and decrypts it. So it will be actually a valid ciphertext. The ciphertext is new, but it is also a valid ciphertext. That is required property by the ciphertext integrity, right? So ciphertext integrity is ciphertext integrity basically is not there, because the adversary is able to come up with such ciphertext which decrypts to some valid message but not seen by the adversary previously. Okay. Now, in case of second construction, E2 is defined as E2 of K comma M is C comma C, where again C is encryption of M with key K by the basic encryption algorithm, and D2 is done in the similar way as the first scheme, but there is one extra check whether C1 is equal to C2. Only in that case, the decryption algorithm actually returns K comma C1. Else it rejects or it outputs bot. Now, to argue CPA security of this modified scheme, the argument remains the same as the previous one, where we say that if the scheme E2 here we say that if the basic encryption scheme is CPA secure, then the modified encryption scheme is also CPA secure, because if it would not have been the case, if we say that the modified scheme is not CPA secure, that means that the adversary is able to distinguish between encryption of M0 and M1 by using the encryption oracle. Okay, and what information it gathers from encryption oracle? It is just again message ciphertext pair of the form M comma C1 C comma C, right? So if the adversary is able to distinguish between encryption of M0 and M1 using this information, then it can surely distinguish the encryption between M0 and M1 in case of the basic scheme E using the encryption oracle. Because there in the basic scheme only M comma C information is visible, and here also M comma C, the same information is visible in the modified scheme. So the modified scheme is basically CPA secure. But in the second construction, we say that it provides ciphertext integrity, because whenever you want to distort the ciphertext, okay, and get some new ciphertext which decrypts to some valid message, then you actually cannot come up with this such ciphertext pair where C1 is not equal to C2, like the previous one. So always there is this check whether C1 is equal to C2, and if C1 is a known valid ciphertext seen by the adversary from encryption oracle service, then it basically has to come up with some new C1 dash, right? Which is not really possible by the adversary. So it ensures the ciphertext integrity. Now we will start this week's topics. So this week's broad topics are composing CPA secure encryption with secure MAC, key exchange protocol, one-way trapdoor function, and cyclic groups. Okay, so you can answer the questions in the chat box, or you can unmute yourself and answer. So first question is, choose the right options for the authenticate then encryption approach, which is instantiated with a CPA secure encryption scheme and an SCMA secure MAC. It is CCA secure but not an authenticated encryption scheme. It does not provide ciphertext integrity. It provides ciphertext integrity. It is not CCA secure. So there are comments about authenticate then encrypt approach. So you can answer one. I'll give you some time to think. Anyone would like to answer? So in authenticate then encrypt approach, what happens is that you combine SCMA secure MAC with a CPA secure encryption scheme. You first take the message, authenticate it to generate tag T, then use this M concatenated with T, the whole thing as plaintext of the encryption scheme, and get the output, right? So that is how you do the authenticate then encrypt approach. Now the options given are, so first option is that it's CCA secure but not an authenticated encryption scheme. Basically what we say is that it is not even CCA secure, because if you remember from the lecture, so there is this discussion on how CBC mode of block cipher is not CCA secure. Okay, so there can be even if your underlying encryption scheme is CPA secure, it may not be CCA secure, right? And in that case, for the particular case of CBC mode of block cipher, you can launch padding oracle attack to retrieve the whole plaintext message block. And now, if you are doing authenticate then encrypt, so basically, if your encryption scheme, the final encryption scheme used is even if it is CPA secure, but it is not CCA secure, then you can easily recover the whole message tag pair, right? And thus the scheme is just comes down to a message concatenated with tag pair, right, which is recovered. And using that, any adversary can surely distinguish between the encryption of M0 and M1, right? So it is not anymore a CCA secure scheme, and so it is not even authenticated encryption scheme also. Uh, so the correct option is, of course, it does not provide ciphertext integrity, and it is not CCA secure. Okay. In the key exchange problem, the goal of the sender and receiver is to agree upon a common public key over a private channel, agree upon a fixed common key over a public channel, agree upon a fixed common key over a private channel, agree upon a random common key over a public channel. So this is very straightforward question. You would like to answer? B, fixed common key over a public channel. Actually, it should be random common key, because every time, like if you look at the key exchange protocol, what it does is that there is two party who are trying to decide upon a key. So this key, for every session, actually the protocol is not deterministically output some key, right? So you run the protocol twice, you will get different key. So both these parties will output the same key in their own, that is okay. But the protocol is randomized, right? So basically it will be random common key, but of course over a public channel. That is the whole purpose of key exchange problem, right? So key exchange problem is the problem where basically you have previously, when doing symmetric key encryption, we always assume that somehow both the parties have agreed upon some secret key K known to only communicating parties, but not any third parties, right? But how they agree upon this common secret key K, that is the problem statement of key exchange problem. So both of them are agreeing upon some common key, okay? But the communication happens through the public channel. Any adversary can see the information which are communicating between sender and receiver, and this whole bunch of information which are seen by the adversary happening to the public channel is called the transcript. So the adversary has access to this transcript, but yet it is unable to distinguish whether given some uniform random key from the key space and the key which is being agreed upon by the two parties, the adversary cannot effectively distinguish between them, right? Okay. So next problem. Let sender and receiver have a pre-shared random AES key K. Then consider the following method of authenticating messages of size which is multiple of 64 bits. To authenticate a message M which is belonging to this symbol, basically what it means that you have L number of, so at max L number of message block, where each message block is 64-bit binary string, right? So containing L blocks M1 to ML, each of size 64 bits. The tag generation algorithm outputs T equal to T1 to TL as the tag, where each TI is nothing but AES of MI concatenate with integer representation of L. So MI is of size 64 and L denotes 64-bit integer representation of the integer L. So this L inside angle bracket is also of size 64. So in total, the input to the AES is 128-bit. So it is 128-bit AES. And accordingly, the tag verification algorithm performs the corresponding verification step. Identify the false statement from the following. So you consider this MAC, this tag generation algorithm, and there are some comments. The above MAC is randomized and hence is SCMA secure. The above MAC is deterministic and hence is CMA secure. The above MAC when used in the encrypt then authenticate approach leads to an authenticated encryption scheme. The above MAC when used in encrypt and authenticate approach leads to an authenticated encryption scheme. You would like to answer? Okay. So basically, if you notice here, this mix and match thing works here also. So basically, it is not even a secure MAC. If you see here, okay, we are not even talking about the authenticated encryption happens or not. If you see, you just take some M1, third and fourth option is same. No, third option is encrypt then authenticate, and fourth option is encrypt and authenticate. They are two different approaches, right, for constituting authenticated encryption scheme using CPA secure encryption and secure. But about this question, just notice that it is this tag generation algorithm is not even a secure MAC, because you just do say take the message as M1, M2 and get the tag as T1, T2, where T1 is AES of M1 with message L. So which is right, which will be 2, right? Okay. So this MAC algorithm, of course, is not randomized here, because with same M1, M2 till ML, you will always get deterministic output, right? But this will not be chosen message attack secure. Okay. Why is that so? You can basically so you can basically do this, right? You take you can just reorder, right? So say M1 and you have message M1, M2, right? And your tag will be M1, integer representation of 2, which is T1, and your T2 will be M2, again integer representation of 2 only. Then T2, T1 will be a valid tag for M2, M1, right? So the adversary is able to come up with a valid message tag pair by seeing previous message tag pairs by querying the oracle. So this is not CMA secure, right? And so this MAC is deterministic, but it is not CMA secure, hence it is not either strong CMA secure. And if the MAC is not secure, then it cannot be used neither in encrypt and authenticate approach, neither in encrypt and authenticate approach. Okay. Hope I am clear. Now proceeding to the next problem. Consider a secure PRF fk 01 to the power n to 01 to the power n, using which we construct a keyed function f dash 01 to the power 2n to 01 to the power 2n, where fk dash x1 concatenated with x2 is equal to fk of x1 concatenated with fk of x2, and of course x is x1 concatenated with x2. Then you have comment about whether f dash is secure PRF or not, and even if it is secure, then whether it leads to CMA secure MAC or not. Okay. So you want to comment about what are the correct option for previous problem? Okay. None of them basically. I just discussed that the MAC is not secure at all. So it is not even CMA secure, and SCMA secure is even advanced concept than CMA security. Okay. So let's say if your MAC tag generation scheme is deterministic, then CMA security implies SCMA security. So, but here in this case, the MAC is not even CMA secure. Okay, the MAC is deterministic, of course, but the MAC is not CMA secure. As I said that, seeing tag of M1, M2, you can come up with the tag for message M2, M1 by just reordering the corresponding tag messages. Okay, so the MAC is not CMA secure, and hence if it is not CMA secure, then it cannot be anyway used in this composing scheme of encrypt then authenticate or encrypt and authenticate. Okay, so none of them are correct. Okay, so coming back to this fourth problem, you want to comment about this security of PRF here. So in case of PRF, just remember that you are allowed to query the challenger with polynomial number of input queries and see the PRF value and see basically either the PRF value for the corresponding input or some randomly generated value from the output space of the PRF, and the adversary's task is to determine whether it is interacting with a PRF or a truly random function. Okay. Now, if it finds some choice of input in order to distinguish between whether it is interacting with PRF or TRF. So in this case, whether it is possible, if you want to comment on that. You can, okay, there is an answer. Seems to be not secure. Yes, you are right. You want to comment why is that? How you can distinguish, how the adversary can distinguish between the PRF and TRF interaction? Okay. So here you can do this thing that the adversary queries with some say x1 concatenated with x2, and if it is interacting with a PRF, then it will get back fx1 concatenated with f of x2, right? Then the adversary can query the oracle with some x1 dash concatenated with x2 dash such that x1 is not equal to x1 dash and x2 is not equal to x2 dash. Then it get back, if it is interacting with a PRF, then it get back f of x1 dash concatenated with f of x2 dash, right? And then the adversary queries with x1 concatenated with x2 dash. And if it is interacting with a PRF, then what it gets back is that f of x1 concatenated with f of x2 dash. And now it matches whether this first part of the output matches with the first part of the first PRF output for x1 concatenated with x2 query, and the second part matches with the second part of the query for x1 dash concatenated with x2 dash. If this matching happens, then it can say that okay, I am interacting with a PRF. Otherwise, although these three inputs are related to each other, the TRF output would not have been related to each other. They would have been truly randomly distributed over the PRF range space, okay, the output space of the PRF. So with non-negligible probability, the adversary is able to distinguish whether it is interacting with a PRF or a TRF. Right? Whether secure means CC or CP. Okay, let me first clarify. So we are here discussing about the security of PRF. CPA security or CCA security comes in the context of encryption scheme. Okay, when you are talking about the encryption scheme, then you know the concept of semantic security. Okay, so what semantic security says is that the adversary will provide two plain text M0 and M1 to the challenger, and the challenger will give back the encryption of either of them. So any one of them. So the challenger will choose some bit B which has value either 0 or 1, and depending on the value of B, it will return to adversary encryption of MB. Now looking at this encryption of MB, the adversary's task is to say whether it is MB equal to M0 or MB equal to M1. Okay. This is the concept of semantic security, and when the adversary has been given access to encryption oracle in addition, then this concept becomes the CPA security. So the adversary's job is to distinguish between encryption of M0 or M1 in presence of encryption oracle service, and this concept becomes CCA security when the adversary has access to an decryption oracle as well. So adversary has access to encryption oracle and decryption oracle, and his task is to distinguish between encryption of M0 or M1. That is the concept of CCA security of some encryption scheme. In context of PRF, we are not talking about any encryption scheme. PRF is a cryptographic primitive where pseudo-random function, right? You are trying to design a function whose output is indistinguishable from output of a truly random function. So this is some function defined here, okay, and the adversary's job is to interact with the challenger, and the challenger may decide in the beginning whether it is going to reply to the adversary with the actual PRF output, that is pseudo-random output, whether or it will decide to give to the adversary some truly random output. Okay, now the adversary will query polynomial times to the challenger, and it will see a bunch of corresponding outputs. These outputs can be generated using the PRF function or some truly random function. And seeing this polynomial number of outputs, the adversary's job is decide to whether it is interacting with a PRF or a truly random function. And the security notion of PRF says that this distinguishing advantage of such an adversary should be negligible. So the adversary should not be able to distinguish with non-negligible probability that whether it is interacting with a PRF or a TRF. That is the purpose of pseudo-random function. The output of PRF should be indistinguishable from a truly random output. Okay. So these concepts are not related to each other. PRF does not deal with neither CPA security, CCA security. Both these concepts are as aligned with the encryption scheme security. Okay, hope I am clear. Okay. Now, okay. Thank you. So coming back to this question, we already discussed that function f dash is not a secure PRF. And if it is not a secure PRF, then this cannot lead to further other cryptographic primitives, say CMA secure, MAC, or anything else. So function f dash when used directly does not lead to a CMA secure MAC. Okay. So basically MAC can be built using PRF. Okay. But if the underlying PRF is not itself secure, then we cannot build any further secure cryptographic primitive based on that. Okay. Consider the following key exchange protocol. Alice chooses uniform k, r belonging to n-bit binary strings and sends s equal to k XOR r to Bob. Bob chooses uniform t, again n-bit binary string, and sends u equal to s XOR with t to Alice. Alice computes w equal to u XOR r and sends w to Bob. Alice outputs k and Bob outputs w XOR t. So description of a key exchange protocol is given here. The correctness property of key exchange protocol says that the sender and receiver independently runs some protocol. There happens some communication between them, and the output of both the protocol on sender and receiver side should output same key k, okay, that they are agreeing upon. That is the correctness property, that they both should output same key, that is ks should be equal to kr, where ks is the output of the sender side protocol and kr is the output of the receiver side protocol. And the security of key exchange protocol says that whatever communication happens between the sender and receiver, that is called the transcript, as I already said. So the transcript is visible to any third party or an adversary who is observing the public communication channel. And even after seeing the transcript, the adversary should not be able to come up with the exact key equal to ks or kr. Or in a stronger security notion, we say that the adversary, when it is provided with either of ks or some uniform random key from the key space, it should not be able to distinguish between them. That is about key exchange protocol. Okay. So anyone would like to just calculate something on their own and say that whether it satisfies these properties of correctness and security here. So S, U, and W are getting communicated through the public channel here. Okay, let me discuss them. Just note that Alice is outputting K, that is okay. We need to check whether Bob, after this key exchange protocol is ended, produces the same key K or not. So what Bob outputs is that, so let's take it from bottom to top. Okay. So we say that Bob outputs W XOR T at the end. And what is W? W is U XOR R. So we are just replacing here W with U XOR R. What is U? U is S XOR T. So let's replace U with S XOR T. So S XOR T, XOR R, XOR T. There are two T. So we cancel them out. So we are left with S XOR R. And then what is S? S is K XOR R. So S is replaced with K XOR R, and there is this another R, so we cancel them out according to the XOR operation property, and we are left with just K. So yes, whatever Bob outputs, that is exactly equal to key K, same as Alice. So the key exchange protocol is correct. Now what about the security? We say that the protocol is not secure. Why? So the transcript visible to adversary here consists of S, U, and W, right? You just perform simple XOR of them, and what you get is XOR U XOR W. That is, you replace S with K XOR R, you replace U with S XOR T, where S is K XOR R. So in in a whole, U is K XOR R XOR T. We are replacing U here, K XOR R XOR T. And there is W. What is W? W is U XOR R. And what is U? U is K XOR R XOR T. So K XOR R XOR T XOR with R. That is W. And you just see that there are how many number of R are there? 1, 2, 3, 4. There are 4 R, so they will get cancelled. How many T are there? 1, 2. 2 T's are there, so even number of T's. So that will also get cancelled. How many K are there? 1, 2, 3. 3 K's are there, so 2 of them get cancelled and we are left with only 1 K. So you just perform the XOR of the transcripts SU and W and you get the key K. So that is known by any third-party adversary who is observing the transcript. So this is essentially not secure. Proceeding to the next question, which of the following is correct? Encrypt then authenticate approach with underlying secure encryption scheme and secure MAC always lead to secure authenticated encryption scheme. Encrypt and authenticate approach with underlying secure encryption scheme and secure MAC always lead to secure authenticated encryption scheme. And authenticate then encrypt approach with underlying secure encryption scheme and secure MAC always lead to secure authenticated encryption scheme. To comment on that, this is very basic question. Okay, so as discussed in, okay, there is an answer. 1. Yes, you are correct. So of course, you have underlying CPA secure encryption scheme and strong CMA secure MAC. Then if you compose them in encrypt then authenticate approach, then you are guaranteed to get a secure authenticated encryption scheme. For the other two approach, that is encrypt and authenticate then encrypt, in these two cases, you are not necessarily guaranteed to get secure authenticated encryption scheme. You may get, but that depends upon the situation. So you cannot say with 100% probability that you are going to get secure authenticated encryption scheme. First option is the only correct option here. PyCPA is a CPA secure encryption scheme over message space MCPA, key space KCPA, and ciphertext space CCPA. PyMac is a secure MAC over message space MMAC, key space KMAC, and text space TMAC. The scheme Pi1 is composed from them using encrypt and authenticate approach. Pi2 is using encrypt and authenticate approach. Another scheme Pi3 is composed from authenticate and then encrypt approach. So there are 3 approaches, Pi1, Pi2, and Pi3 are composed in these 3 approaches. And there are some comments about message space, key space, and ciphertext space of these 3 schemes, Pi1, Pi2, and Pi3. Which of the followings are correct? First says all of Pi1, Pi2, Pi3 have keys of the form K1, K2 such that K1 belongs to KCPA and K2 belongs to KMAC. Pi1 has message space MCPA and ciphertext space CCPA cross TMAC, and MMAC is equal to CCPA. Pi2 has message space MCPA and ciphertext space CCPA cross TMAC, and MMAC is equal to MCPA. Pi3 has message space MMAC and ciphertext space CCPA, and MCPA is equal to MMAC cross TMAC. Anyone would like to answer? This meeting ends, then you can join the same meeting later. So here basically just follow that. Let's say, so all the 3 schemes of course have keys, 2 keys. One is CPA key for the encryption scheme and key for the MAC. And two keys K1, K2, one comes from the key space of the CPA scheme and another key comes from the key space of MAC scheme. That is okay. Now, so first option is correct. About the next three options, so you just note that Pi1 has message space MCPA, which is true because you are doing first encrypt, then authenticate in case of M1. So as you are doing first encrypt, so the encryption scheme space is the message space for encryption scheme is the message space for Pi1 as well. So message space is MCPA. And then you get a cipher text, right, after encryption. And then you are using that cipher text as input to the MAC scheme, and you are getting some tag. And your overall output of the authenticated encryption scheme Pi1 is the ciphertext and the tag T. So the output space for the whole authenticated encryption scheme is CCPA cross TMAC. So you have the ciphertext and the corresponding tag of that ciphertext. So this is the ciphertext space for the authenticated encryption scheme. And MAC is equal to CCPA. Because you are doing first encrypt, then authenticate. So whatever is the output your encryption scheme, that is the CCPA space, that is the same as the message space for the MAC scheme. Because for the MAC scheme, you are using as message the ciphertext itself. So MAC is equal to CCPA. In the next case, which is encrypt and authenticate approach, there you individually perform both encrypt and authenticate on the message itself. So message space remains same, MCPA. And in fact, MCPA is equal to MAC because you are applying the CPA secure encryption scheme on the message M, getting a ciphertext C, and you are also applying the tag generation algorithm of the MAC scheme on the same message M and getting a tag T and output C, T as the output of message and authenticate approach. So your message space is MCPA, which is also equal to MAC, and the ciphertext space is same, that is CCPA cross TMAC. In case of third scheme, your message space is MAC because you are first authenticate, then encrypt. So as you are authenticating first, so your message space should be same as MAC, and then you get some M, T pair and use that M, T pair as the message to the CPA secure encryption scheme. Okay, so your ciphertext space is CCPA because final output of the encryption scheme is the output of the authenticated encryption scheme as well. So ciphertext space remains CCPA, and the plaintext space for the CPA secure scheme is actually message, tag pair. So it is MAC cross TMAC. Okay. So let's proceed to the next. So all of them are correct basically. Coming to the next question, which of the following is or are correct? So padding oracle attack is performed to break authenticated encryption scheme constructed using encrypt then authenticate approach. Padding oracle attack is performed to break authenticated encryption scheme constructed using authenticate then encrypt approach. Padding oracle attack is capable of recovering number of padded bytes in the message, and padding oracle attack can be used to retrieve the whole plaintext block. So as you have seen in the lecture already, that padding oracle attack is just the exploitation of the fact that whenever you use a CBC mode of block cipher for encryption as the underlying CPA secure encryption scheme of your composed MAC, then the fact that the last message block is actually padded is actually some kind of padding depending on the number of required padding block to make the total length of message as multiple of the block size of block cipher, then you can exploit the fact that whenever there is a bad padding, you get the response as some bad padding error. And you can use this bad padding error message to, in fact, retrieve the whole underlying plaintext block. Okay. Now, this padding oracle attack is actually performed to break authenticated encryption scheme, which are constructed using authenticate then encrypt approach. As I have already said that if you have underlying CPA secure encryption scheme and SCMA secure MAC scheme, then encrypt then authenticate approach always gives you authenticated encryption scheme, which is not the case for authenticate then encrypt approach. So the second option is correct, that padding oracle attack is performed to break authenticated encryption scheme which are constructed using authenticate then encrypt approach, because even though you are authenticating first, your final block of ciphertext is just the ciphertext output of the underlying encryption scheme, which is vulnerable to padding oracle attack. Okay. The third option, padding oracle attack, is capable of recovering number of padded bytes in the message. That is true, and padding oracle attack can be used to retrieve the whole plaintext block. This is also true, as I already discussed. And how the padding oracle attack is done, that is clearly discussed in your lecture also. Okay. So you basically check byte by byte. So if you remember the CBC mode of encryption, they are actually, let's say you have two message block M1, M2, and your ciphertext is of the form IV, C1, C2. Okay, and your C2 is basically FK of C1 XORed with M2, if you remember. Okay, so your output of the first block, which is C1, is passed to the second block of input. So C1 is first XORed with the second block of message M2, and C1 XOR M2 is passed to the second FK block, and the output is C2. So while decrypting, so if you just distort C1 little bit to get C1 dash, so your plaintext block M2 becomes some M2 dash, where M2 dash is equal to F inverse of C2 XORed with C1 dash. Okay. As C1 is changed to C1 dash, M2 will also change to M2 dash. And you can exploit this fact when you get the bad padding error. So at which block, starting from the very first block of C1, so you change first byte of C1 first and check whether you are getting bad padding error for the last block M2, and use this information to get what is the number of total padded byte in the last block. And after that, you can even check for all possible number of bytes and get what is the exact plaintext byte value of the original message in the last block of message. Okay, so like that you can actually perform the padding oracle attack. So last three options are actually correct option. Select the correct statement. In a key exchange protocol, the adversary should not be able to guess the key computed by both the parties at the end of the protocol, except with negligible probability, even after seeing the transcript. This is called weak privacy. Second option is, in a key exchange protocol, the adversary should not be able to distinguish the actual key from a uniform random element of the key space, except with negligible probability, even after having the knowledge of the transcript. This is called strong privacy. So this you can answer, I guess. This you can write in the chat box. Okay. So yes, basically both the statements are correct. In case of week, okay, there is answer. I am having question on week 7, fifth question. I think both are cyber text integrity. Shall we discuss about cyber text? First, though, it's not cyber text. I don't know if it is type or not. So it is basically cipher text integrity. Okay, I will come back to question 7 once I am done with the discussion of this week's material. Okay, I will get back to you. So for this question, so weak privacy is where we ensure that the adversary should not be able to guess the exact key which is output from the key exchange protocol run by both the parties. Okay, so coming up with the exact key is possible with negligible probability only by the adversary. This is the weak privacy concept of key exchange protocol. And the strong privacy concept of key exchange protocol says that if the adversary is provided with either output of key exchange protocol or some random element from the key space, the adversary should not be able to distinguish between them. That is more stronger notion of key exchange protocol. So that's it. So these two statements are correct. In abstract Diffie-Hellman key exchange protocol, both sender and receiver have some randomly chosen value alpha, beta respectively. E is a function such that values of E of alpha and E of beta are communicated through the public channel. The final output, that is the key of the key exchange protocol, is f of alpha comma beta. Now choose the correct statements. Given alpha and E of beta, it is easy to compute f of alpha comma beta. Given beta and E of alpha, it is easy to compute f of alpha comma beta. Given E alpha, it is easy to compute alpha. Given E alpha and E beta, it is easy to compute f of alpha comma beta. Anyone would like to answer? Okay. So basically, it is the required property of so we are actually not discussing exact instantiation of Diffie-Hellman key exchange protocol. So when we just abstract that protocol, so we are not exactly defining what function E and function F are. We are just assuming existence of some such E and F. Now, basically what these two parties, say sender and receiver, does is that sender may choose some alpha randomly on its own, and receiver also may choose some beta on its own, and the sender then sends E of alpha through the public channel to the receiver, and receiver sends E of beta to the sender through public channel. Now, in the transcript, the adversary is able to see both E of alpha and E of beta. And then what sender does after receiving E of beta is that it has its own random input alpha, so it somehow provides somehow computes the function f of alpha beta by using its own randomness alpha and the input E of beta which it received from the receiver side. And similarly, the receiver also received E of alpha from the sender side. So using the information E of alpha and the randomness beta of its own, it computes f of alpha beta, and both of them actually outputs f of alpha beta as the final key. Now, of course, if it has to compute f of alpha comma beta, the sender has to, so the job of sender should be easy with the help of these two information, alpha and E of beta. So alpha and E of beta being the information, f of alpha comma beta should be easy to compute by the sender side and for the receiver side also, beta and e of alpha, it is easy to compute f of alpha comma beta. Okay, so these two options are correct. Given e of alpha, it is easy to compute alpha. That is not true, because if it is true, if it is possible by seeing e of alpha to compute easily alpha, then the public transcript that is seen by the adversary, it contains both e of alpha and e of beta. And if it is easy for it to compute alpha and beta from e of alpha and e of beta respectively, then it can know alpha and beta by seeing the transcript, and it can easily compute f of alpha comma beta, which should not be the case because the scheme has to be secure. So third option is not correct. Also, for the same reason, given e of alpha and e of beta, it should not be easy to compute f of alpha comma beta. Otherwise, the adversary would have come up with the correct key f of alpha comma beta by seeing the transcript e of alpha and e of beta. So last two options are not correct. So next question. Which of the following is or are true? A one-way function is easy to be evaluated on some random input x from its domain, but given some random value y from its codomain, it is hard to invert. A one-way trapdoor function is easily evaluated on some random input x from its domain, and given some random value y from its codomain, it is easy to invert with the knowledge of trapdoor information. If a one-way trapdoor function Jane f and inv is defined over x comma y, the function f is deterministic 1-to-1 and onto. If a one-way trapdoor permutation Jane f inv is defined over x comma y, the function f is deterministic 1-to-1 and onto. Anyone would like to answer? Okay. So the concept of one-way function was discussed previously also. The definition of one-way function only tells that given, so what is domain and codomain? Domain is the input space of the function, and codomain is the output space or range of the function. Now for one-way function, as the noun suggests, it is one way. So given x from the domain capital X, it is easy to compute the function f on input x. But seeing some random y from the range or from the codomain of the function, some random y you see, you cannot easily invert it to get back the corresponding x such that f of x equal to y. That is the concept of security of one-way function. So first option is true. In case of one-way trapdoor function, it is same as one-way function, except that there will be some extra information called trapdoor. So without the knowledge of trapdoor, it is hard to invert a random y of the codomain space of the function. So if you were given some y in the codomain of the function, and given that random y, it is hard to invert it to the corresponding x such that f x equal to y if you don't have the information of trapdoor. But if with the information, with the trapdoor information available, it is easy to invert. So one-way trapdoor function just provides this trapdoor thing to invert easily, but without the information of trapdoor, it is hard to invert. So second option is also correct. Third option, if you one-way trapdoor function with this three algorithm, Jane, that is the key generation algorithm, f is the function and inverse is the inverse function. It's defined over x comma y, that is x is the input space and y is the output space or codomain. The function f is deterministic 1-to-1 and onto. So is the trapdoor function, one-way trapdoor function, that is the deterministic function. So for input x, it will always get the same output y, and it is 1-to-1 as well, because if it is not 1-to-1, then there will be some x1 and x2 in the input space, which will which may map to same output y. But then the inverse function, with the knowledge of trapdoor information, it is easy to compute inverse, right? But the inverse operation will then be ambiguous. It may output x1 or it may output x2, but then that is a problem, right? So inverse operation, if you need inverse operation to work properly, you need f to be 1 to 1. Okay, but it need not be onto, because inverse operation allows output bot also. That means that there will be some y in the codomain of function f such that y is not image of any valid x there. So so the function is not onto. So third option is not correct. And in case of trapdoor permutation, all the rest applies same. So f is again deterministic 1 to 1, and it is also onto, because as it is permutation, so basically each of the x in from the input space maps to unique image y in the output space, and there will be no such y in the output space which don't have any pre-image in the input space. So because this is a permutation, okay, so the output space for all the input, each of the output in the output space should have some pre-image in the input space, so it is onto. So the third option is the incorrect option. Rest of the three options are correct. Next problem. Exponentiation operation on some group element means applying the group operation on that element repeatedly. A generator in a group in an element is an element G such that G to the power 0, G to the power 1 till G to the power Q minus 1 are some permutation of all the group elements where Q is the group size. A group is said to be cyclic if it has at least one generator element, and all of the above. Anyone would like to answer? This is question about cyclic group. Right? Okay, so exponentiation operation on okay, there is answer. Third option correct. Yes, you are correct. Third option correct. Even the first two options are correct as well. So if you remember what is exponentiation operation on some group element, so you basically do what, let's say you denote the group operation as dot. Okay, so dot is the group operation. If you remember what is a group, group is a set of elements along with some defined binary operation. Binary means it takes two input, x1, x2, and outputs some y. Okay, so a set of elements along with some binary operation satisfies the closure property. That is, you take two elements of that set, apply that binary operation, and whatever you get as the result is also belongs to the same set. So that is the closure property. Group also satisfies the associativity property. That is, dot being the group operation, x1 dot inside bracket x2 dot x3 is equal to inside bracket x1 dot x2 and then dot x3. Both of them are like this. This is the associative property to be satisfied by group. And there exists an identity element in the group, say I, such that any element x dot I should be equal to x. And there exists inverse of each element x denoted as x inverse, such that x dot x inverse returns the identity element I. That is the property of group. Now, exponentiation on some group element G means that, say, G to the power I, that is nothing but G dot G dot G like that applied. So dot operation applied I minus 1 times with the same group element G. That is the exponentiation operation. So the first option, first statement is correct, that exponentiation operation on some group element means applying the group operation on that element repeatedly. To be more specific, to compute G to the power I, you need to apply the dot operation I minus 1 time with input being G. Next statement, a generator in a group is an element G such that G to the power 0 till G to the power Q minus 1 are some permutation of the group elements where Q is the group size. That is again true because that is the definition of generator of a group. Generator of a group. So generator ensures that you apply the exponentiation operation with I equal to 0, 1, 2 till Q minus 1. So basically for all the possible values of I from 0 to Q minus 1, you get distinct element as the output of exponentiation operation, and as due to the closure property, all these outputs of G to the power I belong to the group G itself, and as all these outputs are distinct for I equal to 0 to Q minus 1, so that will cover all the elements of the group G. Okay. So in total, you can say that generator is a group element such that all of its exponentiation returns some permutation of the set of group elements. Okay. And third option, as you said, it is correct because that is the definition of cyclic group, that a group is cyclic if it has at least one generator element in it. So all the options are actually correct here. This is again a very basic question. Which of the following are examples of cyclic groups? ZP star with multiplication modulo P as the binary operation defined. P is prime. So ZP star means the element basically except 0, all the element in the group ZP, that is 1 to P minus 1, all the P minus element except 0. Okay, so ZP star and dot subscript P means the modulo P, multiplication modulo P operation, so which is a cyclic group. Next option is ZP comma addition modulo P as the binary operation defined is a cyclic group. R minus 0, that is set of real numbers except the element 0 with the multiplication operation, is a cyclic group. And Z plus, that is the set of integers, set of all integers with plus operation, is a cyclic group. Anyone would like to answer this? Okay, there is an answer. Except 3, all are correct. Actually, 1 and 2 are correct, but the fourth option is again not correct because Z plus is a group. Okay, that is true, but it is not cyclic because you see that to make a group cyclic, actually, you need to have finite number of elements in the group. Otherwise, it can't be cyclic, right? Because with what the name cyclic suggests is that you need to get repeated number of, like you need to get the element of the group repeated whenever you reach the limit G to the power Q once. So you start with some generated element G, you get, so you have to have some finite size of group, say Q, and then you can get G to the power 0, G to the power 1, dot, dot, G to the power Q minus 1 as all the group elements, and then whenever you perform G to the power Q again, that is nothing but equal to G to the power 0. So all these elements G to the power 0 to G to the power Q minus 1 will get repeated for all the value I greater than equal to Q. Okay, so you get same set of element again if you continue the exponentiation with larger number. But for that, you need to have finite number of elements in the group. So Z plus is a group, but it's not a cyclic group. But as you pointed out correctly, first two options are cyclic group. They are discussed in the lectures as well in detail, that ZP star multiplication modulo P is a cyclic group, and ZP and addition modulo P is a cyclic group with P as prime. Proceeding to the next question. So let ENC and DEC be a CPA secure encryption scheme defined over key space K, message space M, ciphertext space C. Let H1 M to T is the tag space, and H to C to T B. Two collision resistant hash functions. Define the following two modified encryption scheme. So first scheme is encryption 1 with k comma m equal to encryption k comma m comma h1 comma m. So they are trying to build some authenticated encryption, as is evident, because there is encryption and there is some tag space t. So they are kind of trying to calculate some tag on the message m by doing h1 m. h1 is collision resistant hash function. So the cipher in the first scheme, the ciphertext is of the form c comma t, where c is encryption of k comma m and t is h1 comma m. And decryption is done accordingly, that it first checks if h1 of d of k comma c1, that is the first part you decrypt using decryption k comma c1, and then you check whether that plain text when passes through the hash function h1 gives the same tag c2. Okay, if that tag verification matches, then you decrypt the plain text, which is decryption of k comma c1, otherwise reject. Now, whether this is AE secure or not, the question says that show that both schemes are not AE secure. So for the first scheme, this is easy to see that h1 of m is basically hash of the message m. So whether a collision resistant hash function constructs a MAC, it's not, right? So if you remember the previous lectures on how to construct MAC from hash functions, so there are concept of hash and MAC paradigm, and then you have seen the construction HMAC, where you completely use the hash functions only. So you have this repeated application of Davis-Meyer construction with some input pad output pad thing, and then you basically using the Markle-Damgard paradigm, you first hash and then perform MAC, but all using the hash functions. Okay, so there are concept of building MAC from hash functions, but the hash function itself, which is h1 here, collision resistant hash function, cannot be directly used to generate tag. Why? Because otherwise the you see that the any message m, as it is collision resistant, right? So in let's say you have message, you are encrypting message m twice. So the first, so this is basically encrypt and authenticate approach, if you see. So encryption is applied on message m and authentication is also applied on message m. So this is an encrypt and authenticate approach. And what is the main vulnerability of encrypt and authenticate approach? This is existing here also. The second part will always give you some constant value t for some same message m. Although the encryption can be randomized, but the second part of message m will always be same for same message. Okay, so this cannot lead to a secure authenticated encryption scheme, because whenever you are seeing challenge ciphertext of form c1 comma c2, okay, so you see the part c2 and match whether this hash of m part is hash of m0 or hash of m1. By checking that only, you can easily say whether you are seeing encryption of m0 or encryption of m1. So this is not AE secure. And the second part, if this meeting ends, you can join in the same link. Okay. So in the second construction, it's given enc2 k comma m is given as c comma h2 of c, where c is encryption of k comma m. And decryption is also defined accordingly, that it first checks whether the hash of the first part is equal to the second part. Okay, and DEC of k comma c1 is then returned. Okay, otherwise, if the tag verification fails, for the C1 and C2 part, it rejects the sample. Okay. Now here, if you see, this is like encrypt then authenticate approach. You are first encrypting M to get ciphertext C, and then you are applying tag generation on the ciphertext C. Okay. But as I said that the hash function may not be used directly as tag generation algorithm. Okay. So it may not be as SCMA secure MAC, right? So MAC security says that you are seeing valid message tag query for some chosen messages by adversary, but then the adversary should not be able to come up with some new valid message tag pair in polynomial time except with negligible probability. But directly using some collision resistant hash function to generate tag may not be lead to a secure MAC, and in which case if your underlying MAC is not secure, then your overall composed encryption scheme is also not AE secure, right? So that is the end of the discussion for this part. And now going back to problem 5. So this was your question, right? Okay, let's see. So there are two concepts, CPA security and ciphertext integrity. CPA security part is clear, I hope. Now coming, yes, so let's see that coming to the ciphertext integrity part. So I was arguing that construction to provide ciphertext integrity. I guess in your assignment answer, it is provided that construction 2 also does not provide ciphertext integrity, but I feel like it provides. And my argument, so I can think over it again. I feel that this provides ciphertext integrity. I will argue my part of argument here. So that is, if so the construction 2 is E2 of K of M is gives C comma C. Both the part are same. C is some encryption using the basic scheme E. And then decryption of K comma C1 C2 gives you decryption of K comma C1 only if C1 is equal to C2. Now, in order to come up with some valid ciphertext, say some other C1 dash C2 dash. So for ensuring that ciphertext integrity does not hold, the adversary has to come up with some ciphertext C1 dash comma C2 dash such that C1 dash comma C2 dash decrypts to a valid message. Okay, say M1 dash M2 dash. Now here the adversary will have access to, say, encryption oracle, right? Using encryption oracle, the adversary can see for any message M chosen by it, it can see C comma C corresponding to M. Then it provides some M0 comma M1 of its choice to the adversary, and adversary returns it back encryption of MB. MB can be either equal to M0 or equal to M1. Okay. Now, in case of ciphertext integrity game, I actually did not find any such mechanism by which the adversary is able to come up with thus some C1 dash C2 dash pair. Of course, C1 dash has to be C2 dash anyway, otherwise it will return bot, right? So C1 dash has to be equal to C2 dash. But this C1 dash cannot be anything like in ciphertext integrity game, the adversary is allowed to see any ciphertext, right? In the form C, C. So if the underlying scheme is providing authenticated encryption, that means it provides ciphertext integrity as well. In the modified scheme also, then the adversary cannot come up with some C dash, C dash, which is different from any of the ciphertext that is already visited by adversary, right? Which will give some meaningful message M underline. So that was my argument actually, that if the underlying scheme ensures ciphertext integrity here by seeing some other legitimate ciphertext, the adversary will not be able to come up some other legitimate ciphertext. So, but okay, as the answer given here was that it does not provide ciphertext. Yes.
Yes, ma'am.
Mm-hmm.
Ma'am, my doubt is
Yes.
the first option,
Mm-hmm.
the decryption used in the authenticated encryption decrypted way, right?
Yes,
D1 is decryption of K, C1.
mm-hmm.
Yeah, this decryption have a authenticated encryption technique, right?
This
I mean, ciphertext integrity.
yes, we were
The D
arguing D has ciphertext integrity. Yes.
Yes.
Mm-hmm.
Yeah. From ciphertext integrity game, using any ciphertext, the prediction of the any message is to be negligible.
Right. Right.
Right. This is
what
ciphertext
authenticated encryption scheme says about like the basic
if
scheme.
you any ciphertext, you cannot predict any message. If you predict that probability is negligible.
Right.
Yes. So if you say the second option is ciphertext integrity, if so, then the first option, by the second option, the selection of a message is negligible probability means selection of first option is also maybe 2 times of the negligible.
Right. Okay. Okay.
So
I got your. So yes. I got like you were arguing that the if construction, you were talking about construction 1, right?
Yeah, but yes. I mean, my claim is both are ciphertext integrity.
Yes. Okay. Both provide ciphertext.
You told that the second option is ciphertext integrity, but the first option is not ciphertext integrity.
Yes. So, hello. Okay, I got your point. So basically, the first scheme also, if it would have been not secure against ciphertext integrity attack, right? Then it would not have been secure against ciphertext integrity attack against the basic scheme E, D, right? Because we would have been exploiting the ciphertext integrity attack of the modified scheme to attack the ciphertext integrity property of the basic scheme. So that's how the first scheme also ciphertext integrity.
Okay, ma'am.
Yes, thank you.
Ma'am, one more question, ma'am.
Yes.
Actually, ma'am, how will be the end semester? I mean, end of the examination? Will it be the
Sorry,
like the assignment?
Your voice is getting cut actually a little bit. Can you repeat again?
Ma'am, the
Yes.
assignment questions are having only 5 questions, right?
Yes.
Each and every second. Yeah. How will be the end of the exam, ma'am? The protector exam?
How many questions you are asking?
How many questions and how will be the multiple selection option?
Actually, honestly, I also don't know. Okay, we are just like providing supporting live sessions based on the weekly contents posted on the website. I am not also sure that what will be the end exam questions, how many marks will be there or how many questions, or whether that will be objective or descriptive. I have actually honestly no idea.
Since
But
we
if
are
I
poorly,
if I get to know somehow, then I will let you know. Okay.
Thank you. Ma'am, these questions asked in the week 7. The options is to be correct for evaluation of the mark.
Option both provide CPA security.
CPA security and both are integrated. That's the last one.
Yes. Is it not matching with the answer provided?
For your answer, the second option is correct, ma'am.
No, that's okay. I agree that both the options are like satisfying ciphertext integrity here. So that makes the last option correct. Is that the answer given in the answer posted as well?
The option posted as both to 1 and 2 are provide cyber security and not cyber. I mean CPA. Not. I mean, third option is correct as per the evaluation.
That's the third option.
Oh yeah.
Okay. I will get back to you in the next week. So as of now, I am also thinking that both are satisfying ciphertext integrity, but okay, I will think about it again and come back. Get back to
the
you.
same thing I have also posted in the question session in the course itself as a mail. As a mail, I have sent that the objection in the ask question portal in the discussion group.
Sure. Okay.
Thank you.
Thank you.
Thank you.